Well, I will be presenting the You Agree project, which is a project that it's going to address the risk of the UAS in the airspace. So the You Agree project aims at identifying hazards to safety, security, privacy, or environment due to the UAS operations, and it is going to assess how the U.S. space services can contribute to mitigate the risk that is posed by those hazards. So in this project, we have developed some risk models, which are the air risk model, the ground risk model, and the collision risk. And the mitigation barriers, we have identified them from the Regulation 64 for an initial iteration of the project. And then we have identified the final barriers based on the Chorus CONOPS. So first, I will explain how are we quantifying the ground risk and the UAS ground risk model that we have developed. So when a UAS is flying, it can fall into the ground and cause damage to buildings, infrastructure, people, to the environment, but it can also have some social effects like the noise, and the people may not accept that. So the UAS risk model is based on a simulation assessment in which we take into account the urban environment, the impact energy and dynamics from each UAS. We also have taken into account the building materials and the structure, because if one UAS falls into a building, it's not the same to have a building made for glass. This shelter effect will be lower than if we have another material. And we also take into account the population distribution that we have in each zone, because we can be in an urban area, or we can be in a rural area where we don't have people on the ground. So taking all this into account, we have developed our model, and we have run 1,000 of simulated Monte Carlo simulations. And what we obtain is that first, the buildings can protect more than we at first thought, and this can reduce the consequences of the impact. Then the urban context, it's also important, because it's not the same, as I said before, to fly into a city or to fly into a rural area where we don't have so many buildings or industry. And well, in this risk model, we have also made some human assessment, and well, we have that the UAS can injury, it can have more risk than injury, because it can have environmental effect, because you can have trouble with birds, and it also have some economic impact for people and for society. So for the air risk, we can have many airspace users. We can have the USS, some general aviation, helicopters, eVTOLs, but we can also have wildlife. So what the aim here is to address the probability and the severity of these conflicts. For this, we have taken into account some realistic traffic data from FlightAware. We have made some altitude layers to see where each UAS or general aviation is flying. We have made a severity assessment, which is based on the size of the UAS or the bird or the plane. And well, we have also taken into account the wildlife. We know where some birds can fly, and this is also integrated into our air risk model. So with all this, we estimate the encounter likelihood along one trajectory, and we can estimate how will be the risk, if it will be low because no one is expected to fly there, or if it can be really high because we can have birds, we can have general aviation. And well, the idea of this is that we can have dynamic airspace because this can change over time also. It's not the same flying during daytime that at night. And yes, the idea for this is to just see how one trajectory can be affected by the air risk that it imposes. Then we have the collision and encounter risk that we have developed. And here we have different events that could happen. It's not the same to have an encounter than a mid-air collision that will be fatal, probably. Here we take into account pairways conflict, UAS, and UAS unmanned aircraft. And this model is based in Monte Carlo simulations. We use some trajectory input from UAS and also from general aviation. We generate the trajectory and detect if there is any of the possible events of conflicts, encounter, near-middle collisions, and then we can obtain the collision frequency that in a scenario can be placed. So the inputs for this Monte Carlo simulation are the traffic density in that scenario, the Airspace altitude, because we are studying the below VLL, but also the above VLL. We need for that the traffic mix, because it will not be the same to be also in an urban area or in a rural area. We are not expecting to have the same times of UAS flying both sides. We can also have a layered destructor, which means that we can have, for example, open A1 category flying lower than a specific category. And we can also have the simulation time. It means that we can fly maybe 10,000 flight hours or maybe 200,000 flight hours to have a more realistic approach. And well, we have validated this model with the endo model for the collision, and it's supposed to be really, really similar to the endo model, which is the basis for all of this. And well, we can have the risk, but we need to mitigate them. So what we have identified here are the barriers. These are the initial and the final barriers that we have identified from the 664 and for the chorus. And for the strategic barriers, we have the Flight Authorization Service. We have also included the strategic conflict resolution when when a U plan is rejected. This will help the capacity. We have also included the dynamic airspace reconfiguration, the airspace management, and also the geozones. For the tactical barriers, we have the conformance monitoring, the traffic information for the Regulation 664, and we have included the tactical conflict prediction and resolution with the alerts modeling how the pilot will behave, because all of this is into simulations. So we have also the CNS enablers that will help us have those US-based services. And well, for the pre-flight, we define the conditions before takeoff, and we can anticipate the conflict. So this way we can mitigate the risk. And for the real-time operations, we simulate the detection of emerging conflicts, and we solve those conflicts taking into account the human performance, because it's not the same to have a trained pilot that a novel pilot. What we do is to calculate the risk ratio of the barriers, and we can have with this the combination of barriers that it's needed to achieve the target level of safety that we have in the project. So last of all, what we aim to do is to propose a new operating method that will combine the SORA and the U-Space. What we are doing, or we are aiming to do, is to integrate the UA-grade risk model into a tool for the means of compliance. Then we will also help the pre-flight mitigation, because we will check before flight if everything was as we defined before, to check if we are complying with what we said in the authorization. And this way we can have SORA and U-Space becoming a unitary process. So that's all for UAGRI.